problem, it says we have a piston cylinder device. So I'm going to draw a picture of a piston cylinder. And it says it has refrigerant 134A, so R134A. And it says that it has 0.88 kilograms. So that means that the mass is 0.88 kilograms of the refrigerant 134A. And it tells us that it's at, and this should actually be negative 10 degrees. So I'm going to change that. So this is at negative 10 degrees Celsius. So I'm just going to call this T1, is negative 10 degrees Celsius. Now it tells us the piston is free to move. It has a mass of 12 kilograms and a diameter of 25 centimeters. So I'm going to put mass of the piston is 12 kilograms. And this diameter is 25 centimeters. And it says the local atmospheric pressure is 88 kilopascals, so I'll just put P atmosphere is 88 kilopascals. Now it says heat is transferred to the refrigerant, so we have some heat that's transferred to the refrigerant until the temperature is 15 degrees Celsius. So I'm going to specify that T2 is 15 degrees Celsius. And it says determine the final pressure. So A, we want to find P2. And B, the change in volume of the cylinder. So we want to find the change in volume. And C, the change in enthalpy of the refrigerant 134A. So I'm just going to put delta H. All right. So what we need to do, let's just start with A. So A is says to find the pressure. Well, since the piston is free to move, that means that the pressure at the beginning, so the pressure before we start adding heat, so the pressure before the refrigerant is heated and after the refrigerant is heated is the same. So that means that P1 is equal to P2. So the pressure at state 2 is equal to the pressure at state 1, or the initial state. So what we need to do is calculate what the pressure is, like basically at the start. So we can do that with a force balance on the piston. So here's our piston, and we have the atmospheric pressure, and we also have the pressure from the piston, and the pressure from the piston is equal to the force over the area. Well, the force is, let's just do this like this. So the force is equal to the mass of the piston multiplied by gravity. And then the area is just the area of the piston. So this is pi d squared over 4. So that means that the pressure of the piston is equal to the force over the area. So that's the mass of the piston multiplied by gravity over pi d squared over 4. So we know what the mass of the piston is because that was given. We also know what gravity is, and we know what the diameter of the piston is because that was given. So we can calculate what the pressure is. So P1, actually we're looking for P2, so I'm just going to put P2, which is equal to P1, which is equal to the atmospheric pressure plus the pressure of the piston. So this is equal to P atmosphere plus MP, so the mass of the piston multiplied by gravity over pi d squared over 4. So let's plug in some values. P2 is equal to, the atmospheric pressure is 88 kilopascals, and I'm going to write this as 88 times 10 to the third pascals. That's the same thing as kilopascals. Plus, and the reason why I'm doing that is because when I do the calculation for this, so the pressure of the piston, I'm going to get units of pascals. So I want this atmospheric pressure to be units of pascals as well, so I can just add those together. So the mass of the piston is 12 kilograms. Gravity is 9.81 meters per second squared over pi multiplied by d squared. So we're given the diameter in centimeters, so we want to convert that to meters. So this is 0.25 meters squared over 4. And this works out to, well, we end up with, when we go through this, we end up with units of kilograms, kilograms over meters second squared, which is pascals. So we end up with the correct units. So this works out to 90398 pascals, which is approximately 90.4 kilopascals. So that means that the pressure, so this P2, is equal to 90.4 kilopascals. So we've done A. Now we want to determine what the change in the volume of the cylinder is. So what we need to do, we now have a temperature and we have a pressure. Well, actually, we need to determine, so what we're going to do is determine what state, so basically for state 1, and let's just write this out, for state 1, and I'm going to go here, so for state 1, our temperature is minus 10 degrees Celsius, and the pressure is what we just calculated, so 90.4 kilopascals. And for state 2, our temperature is 15 degrees Celsius, and our pressure is also 90.4 kilopascals. These states, since we have both the temperature and pressure given, known now, we should be able to determine if we have a compressed liquid, saturated mixture, or saturated vapor. And once we determine what the phase is, we can look up the specific volume on the table, and then we can subtract the initial volume from the final volume, and then we can calculate what the change in volume is. So let's go look at the tables to determine what our phases are. All right, so now I'm looking at the saturated refrigerant 134A temperature table. So I'm going to look up the saturation pressure at the temperature given. So the first temperature given is this negative 10 degrees Celsius. The saturation pressure at negative 10 degrees Celsius is 200.74 kilopascals. So at minus 10 degrees Celsius, Psat is equal to 200.74 kilopascals. This means that P, since our pressure is 90.4 kilopascals, and we know that because we calculated it, that means that P is less than Psat, so that means that we have a superheated vapor. So now what we can do is, so that means that we're going to look up the specific volume for this temperature and pressure for the negative 10 degrees and the 90.4 kilopascals. We're going to look that up on the superheated vapor table. But before we go to the superheated vapor table, let's just look at what we have for the second state. And we already know that let's just look it up. So the temperature for the second state is 15 degrees Celsius, which is going to fall somewhere in there, so somewhere between the between 14 and 16. And at this, that means that our saturation pressure is somewhere between 473 and 504. So this means that P is still less than P sat. So that means that at state 2, T is equal to 15 degrees Celsius and P is equal to 90.4 kilopascals. That means that we have a superheated vapor at state 2 as well. So that means that both of our states are superheated vapor. So we need to look up our specific volumes on the superheated vapor table. So let's go to that table. So here's our superheated refrigerant 134A table. And so what we need to do, so first of all, our temperature is negative 10 degrees Celsius and our pressure is 90.4 kilopascals. So if you remember the superheated vapor table, the pressures are in megapascals. So we need to convert this to megapascals, and this is 0.094 megapascal. All right, so then the next step is to find the pressure, like find whichever one of these tables is the pressure that you need, and then look up the temperature and so on. We have kind of a problem here because we're given pressure, so we're given a table with pressure at 0.06 megapascals and pressure at 0.10 megapascals, but our pressure is 0.094 megapascals. So in other words, it falls somewhere between these two tables. So we can deal with this in a few different ways. Probably the easiest way is to just eyeball this, and so let's go through that and then I'll tell you a couple more exact ways. So the pressure here is 0.94 megapascals. So we know that, and let's go to our temperature. So our temperature is negative 10 degrees Celsius. So that means that our specific volume has to fall somewhere between 0.35048 and 0.20743 meters cubed per kilogram. So let's just write this down. So we're given data for pressure at 0.06 megapascals and pressure at 0.1 megapascals. Our pressure is 0.094 megapascals. So that means that our pressure falls somewhere between these two given tables, and the specific volume for the at negative 10 degrees C for P equals 0.06 megapascals is V is equal to 0.35048 meters cubed per kilogram, and our specific volume at 0.1 megapascals at negative 10 degrees C is 0.20743 meters cubed per kilogram. So since our pressure is 0.094 megapascals, that means that our specific volume has to be somewhere between 0.35048 and 0.20743. And we know that it has to be slightly closer to the point, or we know that it has to be closer to the point 20743 because 0.094 megapascals is closer to 0.1 than it is to 0.06. So there's a difference between these two of 0.03 approximately, and between these two of 0.01 approximately. So what we can do is just kind of eyeball this and think, okay, well, come up with something kind of closer to this specific volume. That's not going to be super exact, but if you just need something quickly, that's probably good enough. A couple other ways that you can do this is probably the most exact way is to look at a different table. So you can find, so there's software that tabulates all of these values, and so then you can just you would be able to look up the specific pressure, which is 0.094 megapascals at negative 10 degrees Celsius, and it would tell you what the specific volume is, what the enthalpy is, and what all the other values are. So one software package that you can use for this is Aspen. I'm not going to be showing you how to use that, but that's an option to look up exact thermodynamic data. A lot of this data is available online as well, so there's different ways that you can look this up. So basically, probably the most exact way is to not use this table since the value that you need isn't on this table. Another way that we can do this, and this is probably the best way if you want to get the information off these tables, is we can interpolate. So to do this, we're basically making an assumption that the relationship between these variables is linear. So in order to do that, we can say that V minus, so specific volume, so this is the specific volume that we want, minus the specific volume, the first specific volume. So I'm just going to say this table is 1 and this one's 2. So the specific volume from this table, and we're looking at, our temperature is negative 10 degrees Celsius, so we're looking at that line. And then this is V2 minus V1 is equal to P, and we know what our pressure is, minus P1 over P2 minus P1. So then we can solve this equation for the specific volume because that's what we want. So the specific volume is equal to V1 plus V2 minus V1, and this is all multiplied by P, and I'm just going to take this on to the next line. So this is all multiplied by P minus P1 over P2 minus P1. So, and we could define these, like we can define these how we want. So I said this one was 1 and this one was 2. We could also say that this one is 1 and this one is 2, and we would get the same answer. So just be consistent with how you define them, and you should end up with the same answer either way. So then what we can do is just plug in some values to figure out what our specific volume is. So our specific volume is equal to V1. So since I've defined this particular table as 1, V1 is going to be 0.35048. This is plus, and then we have V2 minus V1, so 0.20743 minus 0.35048, and then this is all multiplied by P minus P1 over P2 minus P1, and so we have our, so P is 0.094, because remember our pressure is 0.94 megapascals, so P is 0.94 minus P1, we're going to use this pressure for P1 since I've defined this table as 1, so this is 0.06 divided by P2, which is 0.1, so pressure on this table, minus 0.06. So then if you work through this, you get that this is equal to 0.23, I actually get 0.2 to 8, but I rounded up to 0.23. So approximately 0.23. And then this is meters cubed per kilogram. Okay, so our specific volume at state 1, and state 1 is T is equal to negative 10 degrees Celsius and P is equal to 90.4 kilopascals. Our specific volume is 0.23 meters cubed per kilogram. Now we want to look at state 2. So at state 2, we have that T, so T is equal to 15 degrees Celsius, and our pressure is the same. So 90, well actually 0.094 megapascals. So we're going to do the same thing, only this one gets even a little bit more complicated because now we have, so now we're looking at a temperature of 15 degrees Celsius. Our table has 10 and 20. So we're just going to have to pick a value here. So I would probably just pick a value that's evenly spaced between the 0.39302 and 0.37893. That's assuming these have a linear relationship, so just keep that in mind. So it's 0.39302 minus 0.37893 divided by 2 plus, and then I'm going to add 0.37893. So I'm just going to use 0.385975 for the specific volume on the 0.06 megapascals, and then for the specific volume on this table, I'm going to do the same thing. So 0.23373 minus 0.22506 divided by 2 plus 0.22506. So this is 0.22995. So now I'm going to do the same thing. I'm going to do this linear interpolation to figure out what the specific volume is at 15 degrees Celsius and 0.094 megapascals. So V is equal to, and then I'm going to specify this table as 1 and this one as 2. So I'm doing the same thing basically. So V is equal to V1, which is 3.85975 plus, and then V2 minus V1, so this is 0.2299395 minus 0.38975, and then this is all multiplied by 0.094 minus 0.06 divided by 0.1 minus 0.06. So this is equal to 0.253 meters cubed per kilogram. So that means that the specific volume at our second state is 0.253 meters cubed per kilogram. And before we go back to the slides and the problem, the third part of the problem asked for the total enthalpy. And so we're going to get that from this table as well, because we have a superheated vapor, and so our enthalpy is right here, so the H. And we're going to read that off the table the same way, and we're going to have to interpolate the same way to figure out what our values for enthalpy are at state 1 and state 2. So at state 1, which for T is equal to minus 10 degrees Celsius and P is equal to 90.4 kilopascals, H1, so, well, I'm just going to say the enthalpy for state 1 is equal to 247.77, so 247.77 kilojoules per kilogram. And then for state 2, T is equal to 15 degrees Celsius and P is, our pressure is still the same, so 90.4 kilopascals. H is equal to 268.18 kilojoules per kilogram. And remember, I'm getting the enthalpy the same way, so I'm doing an interpolation to calculate what the enthalpy is from this table. So at state 1, we determined that V, so the specific volume, is equal to 0.23 meters cubed per kilogram, and the enthalpy is equal to 247.77 kilojoules per kilogram. And then at state 2, we determined that the specific volume was equal to 0.25 meters cubed per kilogram, and the enthalpy is equal to 268.18 kilojoules per kilogram. So now we can finish part B, which was to determine the change in the volume between the initial and the final states. So the change in the volume is equal to the mass multiplied by the specific volume. The mass multiplied by the specific volume at state 2 minus the mass multiplied by the specific volume at state 1. And so this is equal to, the mass is given as 0.85 kilograms. So actually 0.88 kilograms. So 0.88 kilograms multiplied by V2 is the specific volume at state 2, so that's this. So 0.25 meters cubed per kilogram minus the mass is the same, so 0.88 kilogram multiplied by the specific volume at state 1, which is that, so 0.23 meters cubed per kilogram. So this works out to 0.0205 meters cubed. And we should probably round this off to like 0.02 meters cubed. Let's do C. C is asking for the change in the total enthalpy. So this is equal to, and we could have done this here, so mass multiplied by the specific volume at state 2 minus the specific volume at state 1. So I'm going to do that for the enthalpy. So mass multiplied by the enthalpy at state 2 minus the enthalpy at state 1. So this is equal to 0.88 kilograms multiplied by, and then so the enthalpy at state 2 is this, so 268.18 kilojoules per kilogram minus the enthalpy at state 1 is this, so 247.77 kilojoules per kilogram. And this works out to 17.9 kilojoules, and the kilograms cancel, so it's just 17.9 kilojoules.